A mains wireless set will usually work either on alternating current or direct current. There's often a label reading for universal mains AC, DC, and so on. On the other hand, this electric clock will work only on alternating current. If you were to plug it into a direct current supply, it wouldn't go at all. In fact, it would soon heat up and get damaged. Now, why should there be two sorts of current? What's the difference between them? You remember that an electric current is the movement of electrons from atom to atom along a conductor. With a direct current, the movement is always one way, like this. This is the sort of current supplied by all batteries. The electrons flow from one terminal through the circuit and to the other terminal. Now, an alternating current is different. Instead of being a flow in only one direction, the electrons are made to move first one way and then the opposite way, so that the current flows alternately, back and forth. In our ordinary AC mains, this is happening much faster than we are showing it. There are usually 50 complete to and fro movements, 50 cycles as they are called, every second. Alternating currents originate in mechanical generators, from the huge ones in the power stations to the little dynamo on the back wheel of your bicycle. To show you how this happens, here is a generator which has been made as simply as possible. It consists of a coil of wire and a magnet. To get an electric current, you have to move the magnet near the wire. You can see that each time the ends of the magnet pass the coil, the lamp gives a flash. The quicker we turn the handle, the quicker the lamp flashes become, until eventually they're happening so fast that you can't distinguish separate flashes at all, and the lamp seems to burn continuously, just as lamps do on our AC main supply. If we replace the lamp by a galvanometer, you can see that the needle flicks over first one way, then the other, showing that the current in the wire is first in one direction and then in the other, an alternating current. As the ends of the magnet pass the wire, the magnetic force, so to speak, sweeps the free electrons along the wire. But the magnetic force at the two ends of the magnet acts in opposite directions, so that as the magnet spins, the electrons are swept first in one direction, then in the other. So you see that a generator with spinning parts like this will produce an alternating current, though generators can be modified to give a direct current. For several reasons, the big generators for the grid are made to supply AC, because there are many things which AC can be made to do which are impossible for a direct current. The most important reason is that an alternating current makes the transmission of electricity over long distances much simpler. Almost everyone has seen the great towers which carry the current from the generators. Well, if there were no such thing as AC, electricity would not be supplied in this way. There would be no grid taking cheap electric power from big generating stations to homes all over the country. The big towns might have electric lighting and so on, but if this room were in a country district, it would almost certainly be without. In fact, electricity would be a comparatively rare and costly thing. And all because an alternating current allows you to use transformers, which make it possible to send electric power from place to place as a small current through quite a thin wire, instead of as a big current which could only be carried by a thick cable. You see, although you may change the value of a current by means of a transformer, the amount of actual electrical energy always stays the same. That is, if you start with a big current at a low voltage, you can get a small current at a high voltage. Or you can do the opposite. But you will always decrease one if you increase the other. So the power from the generating station is sent through transformers which turn it into quite a small current, but at a very high voltage, often more than 100,000 volts. And at the far end, it passes through other transformers, coming out eventually at 240 volts and yielding enough current to supply a whole town. With direct current, transformers could not be used. the grid line would have to look something like this. To carry the same power at 240 volts, the cables would have to be so thick that, well, as you can imagine, this wouldn't be practical. Although ordinary AC is pulsating too fast at 50 cycles per second for our eyes to notice any flicker in lamps, if we feed this alternating current into a loudspeaker, you can hear the pulsations as a hum. This is one of the reasons why parts of a telephone circuit have to use direct current only. Even a radio, if it is a main set, has to have a device in it to provide DC from the AC mains. There are other jobs for which you must have a direct current. For instance, if you want to charge a battery, it's no use trying to do it with AC. Because although it may be charging when the current flows in one way, the next moment the current is flowing the opposite way and discharging it, and the two just cancel out. However, it's easy to turn AC into DC. We merely pass the current through a device called a rectifier. There are several different types, but a kind you will sometimes find in a garage is built from a stack of metal plates of a special sort. Another kind is really a big radio valve. Rectifiers of this type are used to supply current for electric trains. You see, they're all doing the same thing in different ways. You remember how a turnstile works. You can only get through one way. Well, it's the same with a rectifier. Electrons can pass through freely in one direction only. So that though an alternating current is fed into it, the electrons can only pass through it in one direction and come out moving one way. You will notice that it isn't a smooth, continuous current, but it is a direct current, because it flows in only one direction. For nearly all practical purposes about the house, it doesn't matter whether you use AC or DC. Lamps will light equally well with either. Electric fires will heat just the same. The small electric motors which work most household appliances, fans, vacuum cleaners and so on, are usually universal. That is, they will run on alternating or direct current. But an electric clock will only work on AC. This is because the mechanism makes use of the pulsating beat of AC. Each pulse of current turns the motor a different amount, so that the rate of the clock hands depends on the rate at which the current is pulsating, what is called the frequency of the current. Now, the frequency is controlled very carefully at the power station, where the current is made to run a clock which can be checked by another clock showing a standard time. And the clock in your home keeps exactly in step with the frequency, so that once it has been set, it should never go wrong. This pulsating nature of AC also means that we can use smaller, lightly made switches, like the one on the right here, because AC is switching itself off in between each beat, and so doesn't give a big spark in the switch. Here is an uncovered switch carrying a heavy DC current. You can see the big spark when you open it slowly, which will burn the metal away. But if we use the same strength of current as AC, this time there's nothing to be seen. These lightly made switches, micro-gap switches they're called, are often built into thermostats on electric blankets and electrically heated clothing, or electric irons, water heaters and so on. So you must be careful not to use appliances of this sort on DC, or you'll very soon damage the thermostat. For DC use, different thermostats are used. Both sorts are clearly marked on the tags. These are the main points about alternating and direct currents. AC is supplied on the house mains because it's easy to generate, easy to transform to a higher or lower voltage, and therefore easy to distribute, and it's easy to turn into DC for special purposes.